So we're trying to apply our integration ideas to more and more situations, and they might be very different in nature, but at the end of the analysis, we always discover the same thing, and that is a certain Riemann integral. In fact, the last example, which was the length of a curve, was most challenging among all that we have seen in the rest of them. And as a matter of fact, so we've seen the areas and volumes, and they all work out very simply, producing a Riemann integral. We had to work hard with the length of a curve to discover the Riemann sum. Okay, so remember this. It was a bit of a challenge to recognizing that fraction over there is in fact the difference quotient, and then the limit of the difference quotient is the derivative, and the result was a somewhat complex formula at the end of this analysis. Now, so much simpler was with areas or volumes, and even with the center of mass. Okay, now we are in a place, once again, it's very different in nature, but the result is quite predictable in terms of the recognizing the Riemann sum. So as you can see, that's what we have at the very end. Let's take another look at what has happened here. So we're looking at the simplest situation first, and that is when the flow does not vary from point to point. The question is the same as how much water will cross that line over there, the red line, when the stream is initially identical through all the locations on the stream on the line, and the answer is it's simply the product. You multiply the velocity of the field by the width of the canal or a pipe. Okay. And then, so that's what we see here on the left. It is the most trivial situation. There is no variability, but you can imagine that either in a canal or in the pipe, the speed might vary, which is what this picture illustrates. And then the question remains the same: how much water you're going to have. One way to visualize it, literally, that picture that we see, in fact, indicates how much water has crossed. It is the longer the arrow is, the arrow represents the speed, okay, and the longer that arrow is, that much water has crossed the line at that particular location, right? So, and then no surprise then that we end up with a summation over there that resembles the Riemann sum to begin with. And why does it resemble so much? Because you could think about it as if, here's another picture, slightly better represented here. So I just want you to look at the picture, the one in the middle and one on the left. So as you can see, we have variable speeds. Well, actually, let me explain first what we're looking at. Imagine that once again we have this is our canal. Okay, and then remember how we did last time. We have various gates for each of the various possible different width gates through that line through which the so it's like locks on the several different gates side by side. Okay, and then the longer arrow indicates faster speed through that gate, based on whatever reason, and then that's the picture in the middle, and then what's picture on the right is literally how much water has passed. It will depend on through each gate. So still we have still these are the gates. If I'm doing it right, yeah, one gate, another. So these are how the gates are separated, and then what do? I take the width of the gate and multiply it by that speed, the height of the length of that arrow, and I end up with literally this visualization of my water. So this is how much water has passed through the first gate. Then the second rectangle, once again, the width times the the speed of the water, that's how much passes through the second gate, and so on. And no surprise, not only the picture, but the formula, not only the formula, the picture also produces something that is very much like the Riemann sum. Okay, so that's what we're seeing here, right at the bottom. Summation of different values of the velocity depending on location, not on time, and the width of each of those little gates. Okay, this is the Riemann sum, so we know what's going to happen next. But before we go into the limits, let carry out a simple computation to make sure that this makes sense. So suppose we have two gates. We have two gates. What happened here? Okay. We have two gates like this, equal width, and suppose the speed here, or rate of flow, speed is say 1, and here speed is 2. Okay, so this is the width goes from 0 to 2, and this is 1. Okay, so this is the description of our situation. The width of the canal is 2. In fact, that look at this line. I guess I should have mentioned that. So these gates, you can think of it as if they continue on into the rest of the canal, because there is no left-right motion along the canal. They all go straight forward. So you can just as well imagine that those separate, the gates are not just short, but rather continue on through the canal, and then the motion is entirely independent. And that's why you have that picture on the right. In another way to see it is if you have like a different color of the water before the gate, before the locks, and then when you open the locks, the water flows through the gates at different speeds, and it colors the water behind that line. Okay, so and that's that blue color on the right is that's how far the water has progressed, and that tells you how much of the water has crossed the gates. Okay, so that's what the simplest example. You have 2 and 2. The speed is 1. If you want to visualize it, then this is it. 1, and this is 2. 1 and 2. So visualize the speed, and then it is exactly gives you the amount of water that has crossed each of the gates. So the total is what is it? 1 times 1 plus 1 times 2. Let me put it in the right order. So the total is each of them is the speed times width, and then I have 1 times 1 plus 2 times 1. The speed is 1 and 1, so the first pair of numbers are these are the speeds, and these two are the widths of the gates. I gotta ask that person, excuse me, you gotta close the laptop, please.
Sorry.
And so the end result is 3. So what is the meaning of 3 geometrically? So we are looking like kind of a situation that is more or less familiar, or it is a reasonable real life situation, but the interpretation we're trying to work our way all the way back to mathematics, and one is algebra, but another one is geometry, and the geometry is what is the meaning of 3? So you see that 3 on the picture. What's the meaning of 3, geometrically speaking?
The total amount of water that's passed.
Right, no, that's what I meant is real life where you have some kind of device measuring the amount of water passing, and that's what we have discovered here algebraically. But you can see the 3 on this picture, ignoring everything, the setup and the whole locks and water thing. What is the meaning of 3?
The area.
It's the area. The area of the 3 rectangles. Well, two rectangles. Why 3? 2 rectangles, right? So two rectangles. Okay, so when we have three rectangles, you will have three terms in your Riemann sum, and so on. So that is predictable. This picture will tells us what is going to happen every time you have any kind of variability. You can have as many gates as you like. You can have a variability of the speed through each of the gates as much as you like. But now the end result will be here when ultimately there is a possibility that there are no gates. Okay, and rather the speed varies continuously. Okay, so that's the challenge of that we face in calculus is continuous change rather than incremental. So this is an incremental change of the speed, and we were able to imagine simply that there are two gates, and it's like there are two pipes side by side just as well, or n sides pipes side by side, and we just compute how much water has passed through all these pipes simultaneously. That's very predictable multiplication followed by addition. But what if the speed changes continuously? Then what do I mean by that? It means, say, so it's same log, okay? And well, it's not a log anymore. It's hard to think of it as a log, but we have some kind of line where, and through that line we have water passing. And suppose it varies from 1 to 2. Okay, so speed varies from 1 to 2. How it varies, how about hypothetically, it varies linearly. So speed grows from 1 to 2 linearly along the line that crosses our canal. Okay, so this is our canal, and this is how you visualize what's happening. But it is not 5 gates, any level of 5 gates or 5 separate pipes there. It is literally you can keep going, and there will be another one in between like this. Okay, just hoping that it's a straight line. It doesn't really look like a straight line, but roughly like this. Okay, like this. Okay, so so the question remains the same. What is the amount of water that is crossing the line per unit of time, or has crossed that line over some known period of time in the past? Doesn't matter. It is fully determined by the setting. And so suppose we have, once again, from 0, so this is the y-axis, this is 1 over here on the y-axis, 2 on the y-axis. On the x-axis, we run from 0 to 1 to 2 again. Okay, so what is the answer? So once again, think about it as if it is well, maybe the water is being colored as it passes through the red line, okay? And then so that front is marked, and then as it flows, the new front. So this is the initial front of the water, and this is the new front. Okay, so you see where every point, every molecule of water has moved. Okay, and so one front, which was perpendicular to our river, our canal, becomes this sloped line. Okay, so the way to measure then the amount of water is what? Pretty much the only way to do it. Well, you can look at it. Let me try to look at it this way. So from the side, this is the water that actually crossed the line. So once again, this is my initial. This is the front. Okay, and now we are here. That is the where it ended up. Okay, so we are talking about the amount, we're talking about the volume, so we are talking about literally the volume of this kind of a trapezoid, or not a trapezoid, the word is prism. So we are looking at the volume of this prism, and the width is the same, so that's what makes it prism, but really what, well, you might not know, so the answer is the volume. The volume, well, it's not the answer yet, but the volume of this prism gives us the volume of the water. And so what is it? How do you if you know how we compute volumes of prisms, or we actually did it. Yeah, well, we totally did it. Remember how we computed volumes by cross sections? Volumes by cross sections. So and let's cross like this. So volume is the integral of the cross sections. So I choose to cross sect them by horizontal planes. So what the cross sections do we get every time we cross it like this? Oh, you get a trapezoid, that's right. So, and in fact, not the trapezoid. There's only one trapezoid, right? It's an identical trapezoid because that, well, by the way we build it, we assume that our canal is, well, it is a kind of a rectangle at the bottom, so flat bottom, flat top, and vertical walls. Let's say the walls have width or height 1, so the depth of the canal is 1. And then, okay, so the cross sections are the trapezoids. And so the volume is then equal to what? The trapezoids, not just variable trapezoids, exactly the same trapezoid every time. So the area of the trapezoid times the height, which is 1. So the area that you can integrate it, if you don't believe me, but certainly that easy to discover apart from integration. So the area of the trapezoid times 1, which is the height, well, times the height. In other words, it's simply the area of the trapezoid. Okay, so the area, and the area of you can be, well, in a minute we'll get to that, the area under the graph of what, of that function that's plotted in yellow. Okay, so which is for us to discover what it is. It is that yellow line represents simultaneously the new front, but it also represents the function of which is the velocity. So it is the graph of the velocity. So see those velocities, those arrows, they are the ones that give you the new front, and which one is the interpretation doesn't matter. It's the same function, and that function will give us through integration or otherwise will give us the area, and that will give us the volume. Okay, so we're not going to integrate this because it is a trapezoid. So in fact it has 1 here, 2 there, so 1, 2, 2, and well, that's it. Okay, so that is my trapezoid. We can find its area, and so you remember how we find it? A trapezoid with the base 1 and 2 and the height 2. The height is that perpendicular part is called the height. So remember how we do it?
You take the average of the bases and multiply it.
That's right. So it will be the area is the average of the bases times the height. So in this particular case, we have then average of the, so it's 1 plus 2 over 2 times 2, so it's 3. Okay, so a predictable answer in a way, well, I'm not sure if it is how predictable it is, but what I want to point out, it is the answer is the same as in this case. So as if you have only two gates and they have constant speed through each of them, 1 and 2, and the end result is 3. But you can also think about as if the velocity is changing continuously and the result is still the same. Acquired through our knowledge of Euclidean geometry. Okay, so next, and then naturally is this is not good enough because it only works out when we recognize the shape. We recognize the shape as the trapezoid, we knew the formula, and we have the answer. Calculus allows us to do the same problem every time whenever the arbitrary shape, as long as the function is not too complicated and we're able to integrate it, we can find the answer. But first, let's continue and finish this part of the formula. So, well, I just as well start over. So we suppose that, well, this is the picture I will be referring to, these two. But this time we are not thinking about the gates. We are moving towards the continuously changing speed. And then these arrows are samples, no more than samples. And as such, they produce that Riemann sum on the right. But what's behind, what sampling means, it means that there is a graph here somewhere, like this maybe. Okay, and we are just, it's as if we have some kind of device that measures the speed in these 5 locations. And based on that, we draw those arrows, we build Riemann sum on the right. But then we keep going and improving with putting more and more detectors in it, the detectors that detect the speed, and then they will take the limit, just as always. So let me write it out. So suppose AB is the cross-section of the canal, or pipe if you prefer. Okay, so then and also suppose that y equal f of x is the speed of flow at location x on the cross section. Okay, so then we proceed on to create a partition of this interval. So like this, x naught is just as always, repeating the same thing. So that is a partition, and then into our gates, if you like, and then we also sample f. So we'll have in each of the interval we will put one sample. So it will be C1, C2, Cn within each of these intervals. Okay, so once again, xk minus 1, xk. Within the interval there is somewhere c sub k, and as always this is denoted by delta x sub k, or simply delta x if the gates have the same width. Okay. Okay, so that's the setup. Then what we do is then the flow through say xk minus 1 xk is the sampled speed c sub k. Okay, so our speed is sampled over here, and then you can think about it as if once again we have an arrow here, and then you multiply by the width times the width, which is delta xk. Okay, so flow through each of these is that. The total naturally is simply the sum of those. Sum f of c sub k delta xk, k from 1 to n. Okay, then the Riemann sum of f Okay, and finally this is all good for approximations, by the way. So if we needed to compute something, not compute something, but suppose we're getting literally a data from our receptors or those detectors on the canal, what do we do to compute not the compute, to approximate the flow? That's how you take for each of the detectors and the gate that they serve, multiply the speed times the width of the gate and add together, and you have your approximation of the flow. If you want absolute accuracy, which might be necessary, then you take the limit. Okay, so then we let delta x go to 0, and we have the end result is naturally the limit, like this, k from 1 to n, delta x k goes to 0. So we improving partition, we refine partitions into thinner, shorter and shorter intervals. Okay, the summation remains the same. And but then we know that the end result is, I put it on the left or on the right, we know that if the limit exists, then we have an integral. As you can see, the integral is right there. We didn't have to do this time, unlike last time, we don't have to do any extra work in algebra in order to recognize the Riemann sum. It is the Riemann sum right away. And the answer is then a simple Riemann integral of this function. Okay, so we certainly can reproduce the result from the last example very simply. We just integrate the linear function. Okay, so well, probably worthwhile. So if f of x is equal to, what was it, x plus what was it, 1 plus x over 2. Wait a minute. So this is my function. It passes through 1 and through 2 here. So it is, what's the slope? The slope is 1. So okay, I'm sorry, the slope is 1/2. 2 and 1. So the slope is 1/2, and so the formula is indeed x plus 1/2, or 1 plus half x. So this is passing through 1 and at slope 1/2. That's what we're getting. And so the integral is 1, 2. Okay, so you can just the flow then is the integral from 0 to 2, 1 plus x squared dx, integrate x plus x squared from 0 to 2, and yeah, and so we get hold on a second, from 0 to 2, 1 plus x over 2, hold on, this is so over 4. Sorry about the integration. So if I plug into 0, I'll have 0. If I plug in 2, I have 2 plus 4 over 4. So the answer is 3, as planned. So as you can see, we don't need geometry in order to answer the question, but certainly in the exercise that you're going to be dealing with, there will be more complex functions to deal with, and the regions might be slightly more different, but really there is no challenge as far as the integration is concerned. It's only the setup and understanding what's going on and turning words into formulas. That's the biggest challenge usually in all of these applications. Okay, so then in general, function could be any. I didn't plot it here, but you can imagine what is going on. Maybe I have another picture here. Well, here's a picture. Okay, so same velocity in the along the canal, and a different velocity across the canal. And then you can see that that velocity is, if it changes continuously, not incrementally, gives you a curve. And that's the curve on the right, the red curve, gives you, on one hand, it is the formula, it is the graph of our functional velocity. On the other hand, it is the front as it has moved from, so as you can see, the picture in the middle has the original front in red, and then the red picture on the right is where it ended up. Okay, so straight, and then it moved forward at a different rate. Okay, and then the colors, my colors are much better than this. Then this is the amount of flow. That's what we have found. Okay, so but there is another interpretation of the same exact thing. Is as always the case. We are ending up with Riemann sums, but there is an interpretation of even the metaphor of the canal. Okay, so well, I'm giving you two new metaphors, producing the same results. So what if the velocity is the same, but the density varies? That's what you see on the right. So the density varies from left to right. It's low density, then darker color is denser density, and then once again very light, and then it is denser, a bit denser. So even though the velocity is then constant, so that's the point. The velocity might be constant, but the density varies, which means that there will be more water passing through the gate where it is denser. So then we integrate, instead of integrating the velocity function, we're integrating the density function once again across the that line over here that we're facing. Another interpretation, yet again, once again the speed is uniform, and the density is uniform too. But the bottom of the canal is curved. Well, that's the picture, the one in the middle. Okay, so once again, even though the surface velocity or the horizontal velocity everywhere is the same, but because the depth is higher at that spot over there, there will be more water crossing again. So either you integrate density, you integrate the depth, or you integrate the velocity, and the result is certainly the same. Different circumstances, the result is gives you the flow rate through this opening. And mathematically, there is whatsoever no difference between all of these, because you end up with simply integral, and the only question is how you interpret the function. So once again, you interpret it as the velocity depending on the location on the cross section. It is then density that depends on the cross section, location on the cross section, and thirdly is the depth of the canal at that location. Okay, so all three are exactly the same. Okay, so that's good news rather than something to worry about. So the computations are naturally the same. Mathematics is exactly the same, as long as you so you pick one interpretation that you want. But certainly the question could be, what if let's say we have velocity varies as well as the density. Okay, that would be a challenge. And what if velocity changes, density is changing, it changes as well as the depth? Okay, so what is the answer? How will you handle that? Well, that creates like a function of two or three variables. So we have one function of one variable, which represents one of those three things, depth, density, or velocity, and you integrate one at a time. If you have two variables, well, then you have to integrate with respect to each of those variables. Okay, so that's what multivariable calculus is about. If more variability, more parameters, more variables, and then there will be as well as integration with respect to each of them, there will be differentiation with respect to each of them. But so we are getting there. We're getting closer to that. Okay, so there are a bunch of interpretation of this stuff, including one more thing I suppose is you can think about actual pipe, round pipe, and then the velocity varies in the radial way from 1 to So maybe very fast in the middle, and then faster and faster, slower and slower as you move towards the wall of the pipe, and then once again you'd have to end up simply integrating this function. Okay, so let's move on from this. And the next topic is will be once again, it's like a physics related, I suppose, but the mathematics is the same. We just have to see all the not all, which is impossible, but at least as many as possible of these applications, or if you prefer, you can think of these as interpretations of the mathematics. So you can interpret this way, that way, in 100 different ways, and you just you know that there are more of those, and you just might be up to you to recognize that what you're looking at is the mathematics is familiar. You just may have never seen it under that angle, but if you see a few examples, then that should be helpful. Okay, so let me turn to the next topic, and the next topic is work. Okay, let me try to start in here. Notebook. If it works. Try again. Does it work? Does it work? No, it doesn't work. Okay, maybe next time. Okay, so I'll continue with this one. Work. Okay, so work is of what? Work of a force, specifically. So you're moving through space, and then you might be subject to forces, and you overcome those forces, and then you either work against the force or the force works against you. Either way, it doesn't really matter. The amount is the same. So it's then everything depends on two things: your motion, as well as the amount of the force. So one picture that here it is. Well, there is no actual person to worry about it, but it is nothing but a ball thrown in the air, and then whether it goes up and down, just like straight up. It doesn't really matter because there's only one force in action. Only one force in action, and that force is the gravitational force over there. So as you can see, then look at just there are two cases then where there are two halves of the trip. Once you go up and then you go down. So the force of the gravity works downward, which means that when you're going up, the ball is going up. It goes against the force, and as you can see, that's what we conclude, that the work is negative. And when it's going down, your displacement, that's what D stands for, it is going down, and therefore the work is also considered to be, and then the work considered to be positive. Okay, so it is, in fact, you might remember that it is a simple multiplication, right? So the displacement times the force. Okay, so as long as you keep track of which way they align, it's no trouble. The challenge will appear a bit later when there will be variability of you can actually have variability of both the force and the displacement. So you might be moving like this, as well as force might be changing. This force is fixed, unchanging, because as long as we stay close to the Earth, it is assumed that the gravitation is exactly the same. But if you throw, not a throw, but send a rocket, then away from the Earth, then the gravitational force of the Earth will be declining, and therefore just a simple multiplication is not going to work anymore. you're already guessing what is going to happen. We're going to end up with a Riemann sum, right? So addition followed by multiplication followed by addition. That's the idea of the Riemann sum. So in fact, let me do that picture that we had just a minute ago, and repeat it. So how? Okay, so the picture will be the same, but the story is entirely different. 0, 1. So this is my trip. Okay, and then I am working against or with the forces 1 and 2. So during the first half of my trip, this is 2, I'm sorry, so from 0 to 2, during the first half of my trip, I was the force was working with me in the same direction, like think wind, a wind pushing you back in the pushing you at your back. And suppose that force was 1, and then the second half of the trip it has become 2. Okay, so so then the total work is equal to the work during the first hour plus the work during the second hour. So it will be the same story as we just had: 1 times 1 plus 2 times 1. Okay, so force and force. These are force. This force has changed because, well, the wind simply changed. It strengthened, and then what is these 1 stand for? And there's not time. This is not time. This is the displacement. So in other words, so it's that x-axis here is not what you see half of the time or all of the time in calculus 1, when the x-axis is in any kind of application interpretation is time. Okay, this isn't time. This is actual location. So you move from location 0 to location 2, and or they're consecutively from 0 to 1, from 1 to 2, and therefore they are two separate situations. And work was during the first hour is 1, and during the second is 2, and so total is 3. Okay, so and then we are following the same procedure, which if you find it repetitive, it is a good thing. So we have once again 1 and 2. This is 1 and this is 2. And to represent what? To represent this sum on the right, it is 1 times 1, this area, and then 2 times 1 is that area. So the height is 2. The height is 2. The width is 1. Here the width is 1. The height is 1. Okay, so 1 times 1 plus 2 times 1. Okay. And then we realize that certainly from the point of view of mathematics, it is the same story. It is summation, multiplication followed by summation. It is if there are more changes, and during that period of time maybe the wind has changed not 2 times but 3 times or 5 times, you know what's going to happen. There will be simply more terms in your Riemann sum. So this is already the Riemann sum. And then in general, you just will have more changes, more terms in your Riemann sum, but they have the same structure of force multiplied by the displacement. And you keep adding together as many times as necessary. So so any picture that we have seen today would do. Not this one, not that one, not this one, this one. Okay, so so that arrow may be not very descriptive anymore, but because it's kind of you're moving this way. That is our motion along the x-axis, and then those magnitudes are not velocities really. They in fact either aligned with your motion or against your motion. So when it's these values of my function of force positive, it will be going left-right along the x-axis, or if the values are negative, it will be against it. But other than that, as you can see, what's on the right is closer to our story. It is the width is of each bar represents the displacement, how much distance you have covered, and the height represents the force you have to deal with. And then you multiply, getting the work, the total work. Okay, so skipping to the next level right away, we're going to consider the case when the force is changing continuously, not incrementally. And I am doing on purpose, once again, exactly the same story as before, and that is the force is changing from 1 to 2 linearly over this period, over this interval from 0 to 2. Okay, so something that we had just a minute ago. Okay, so the graph then looks like this, from 1 to 2, like this, a straight line. This is 1, this is 2. Okay, and then where are our is our work? This is more complex, at least the way I see it. I cannot have a visualization as I had with my flow. So remember, with the flow, we had exactly the same story right here, exactly the same story, 2 stories, and I was able to visualize the amount of water passing through those gates by this prism. Okay, and then we computed the volume of the prism. Unfortunately, that is almost literally visual. We can actually almost see it in real life, a kind of water that passed through the gate in the forms of prism. Okay, we don't have this luxury here anymore because, well, force is a more complex concept of physics. So all we have to do then to rely on then we have to go back and rely entirely on mathematics. However, the answer will be certainly the same. You can already guess that it's going to be the area. So the answer is still the area, and it's still equal to 3. But we don't have this luxury of visualizing this area and just pointing out what it is, because like I said, the force and the work are concepts that not easy to visualize, unless, well, you could try to visualize it if your work is actually something that you're dealing with is something more tangible. So in fact, there must be, I will think it through, but there must be some work, or you think about it as well. Suppose once again we have a crossing of water through the gate. The amount of water that has crossed may correspond to work performed by something. For example, there might be pushing something from behind, pushing it, and then the amount of how far you have pushed it is multiplied by the force will give you the work of that force. Okay, so that way, if you actually pick not an abstract force, we don't know what that force is. But what if we take a specific force, and that is force of the resistance of this air, of this water, that makes the work perform that work, that force to perform that work. Then you can actually see this trapezoid as work. Okay. Okay. Thank you.